All right. 7, 8, and 9, again, we're doing the chi-squared test of independence. Westminster Financial has released a summary of investment package information from the past fiscal year. During this time, Westminster provided a choice among 12 pre-designed investment packages. Westminster classified the packages into 3 categories according to the risk: risky, moderate to mixed, and conservative. We're interested in the possible relationship between the age of an investor and the riskiness of the investment packages she chooses. Table 1, a contingency table, gives a summary of the information released by Westminster regarding the age and the riskiness of the investment package for a random sample of 150 investors. Each cell of the table contains 3 numbers. The first number is the observed cell frequency. The second number is the expected cell frequency, under the assumption that there's no relationship between the 2 variables, riskiness of investment choice and age of Westminster investor for this past year. The third number is the value that we've been calculating. The numbers are labeled total, are the totals for the observed frequency. Fill in the missing values for table 1. Round your expected frequencies to at least 2 decimal places and round your other values to 3 decimal places using the 0.1 or using the 0.10, the 10% level of significance. Perform a test of the hypothesis that there's no relationship between the 2 variables, riskiness of investment choice and age of Westminster investor for this past year. So, in my table, I have right here, now we are basically combining what we did on problems 1, 2, and 3 with what we did on problems 4, 5, and 6, and just making one great big long problem. So, when we fill in our table, again, we're going to take the row total divided by the column total, or the row total times the column total divided by the sample size. That's going to be the top value. The top value is what we did on problems 1, 2, and 3. Row total times column total divided by my, that was supposed to just be column total, total sample size. So the top numbers are what we did on problems 1, 2, and 3. So I'm just going to go ahead and do the top numbers first. I'm going to do them all in red, and then I'll switch colors for the bottom. So on the first one, my row total is 36, my column total is 50. So 36 times 50 divided by my sample size of 150. If you go ahead and do that calculation, 36 times 50 divided by 150, you get an answer of 12. So 12 goes in your top box. I'm going to go ahead and do the top box on the next one. So again, my row total is 36. My column total is 68 divided by my sample size, which is 150. So 36 times 68 divided by 150 would be 16.32. So 16.32 going to go in that top box. Going to do the same thing here. In my top row there, I'm going to do my row total. My row total is 57 times my column total, which is 50, divided by my total sample size, which is my 150. So 57 times 50 divided by 150 comes out to 19. So 19 would go in that box. And then for the last one on there, top box here, my row total is 57. My column total is 68 divided by my 150. So if you take your calculator, 57 times 68 divided by 150 should give you 25.84. 25.84. All right. The bottom ones we're using that formula, FO minus FE squared divided by FE. So these are the ones we did on problems number 4, 5, and 6. I'm going to switch colors here. So when I'm doing these ones here, I'm going to put them in green. So my observed frequency is 10 minus my expected frequency is 12. 10 minus 12 squared divided by 12 would be the number for the first box. If I do my calculation there, I get 0.3333, so forth and so on. So we're going to put in 0.333 because it says to round it to 3 decimal places. Make sure you don't think these are negatives. There, I'll make it an asterisk instead so you don't think it's a negative. On the next one, my observed frequency is 19 minus my expected frequency, 16.32. I'm going to square that and divide it by my expected frequency of 16.32. If you do that calculation, you should get 0.440. 0.440. Punch that into your calculator. Make sure you know how to get that number. The next box. Here I'm doing this one. My observed frequency is 23. My expected frequency is 19. So 23 minus 19 squared divided by 19. 23 minus 19, and then square that, divide that by 19, and you get 0.842. 0.842 goes in that box. And the last one on that part, we are going to do my observed frequency of 29 minus my expected frequency of 25.84. I have to square that and divide it by my expected frequency of 25.84. So 29 minus 25.84, you're going to square that and then divide it by 25.84. When you do that, you should get 0.386. 0.386. All right, so down on the bottom part then, on the second table, table 2, first of all, it's going to ask you what kind of test statistic you're going to have, and it's going to be chi squared. Also, every time we have chi squared, we have to have the degree of freedom. So, the degree of freedom, I'm going to write it up here, is the number of rows minus 1 times the number of columns minus 1. So in this case, I would have 1, 2, 3 rows. So I'm going to have 3 minus 1 here. I have 1, 2, 3 columns. So I'm going to have 3 minus 1 there. Well, 3 minus 1 is 2, 3 minus 1 is 2, 2 times 2 gives me 4 degrees of freedom. 4 degrees of freedom, because I have to take that 2 times this 2 that I got here. Number of rows minus 1 times the number of columns minus 1. The value of my test statistic. If I'm going to find the value of my test statistic, I'm going to add all of the FO minus FE squared over FE numbers. So that means I'm going to take this one plus 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 this one. You're going to add up all 9 of those numbers. So 0.333 plus 0.440 plus 0.060 plus 0.842 plus 0.386 plus 4.216 plus 0.211 plus 1.320 plus 5.055. I got to add all 9 of those numbers up. If you add those numbers up and round to 2 decimal places, you should come up with 12.86. 12.86. This one is asking for the critical value, not the p-value, so we're going to do chi squared. Chi squared sub 0.10, or not 0, yeah, 0.10 with a degree of freedom of 4 that we figured out here when we did the number of rows minus 1 and the number of columns minus 1. So chi squared sub 0.10 with a degree of freedom of 4. Have to do that on your Alex calculator, not your regular calculator. So if you punch that in on Alex, you should come up with 7.78. 7.78 for my critical value. So again, on this one, it didn't start out by asking you what the null and the alternative hypothesis is. On these ones, my null hypothesis is always going to be that it is independent and has no relationship. My H1 is going to be that it is not independent, so has a relationship. I can't spell. I spell it over there. Ship. Yeah, you fix that and spell it right. So, my null is that it's independent, doesn't have a relationship. My alternative one is it's not independent. Again, when we do these ones, my null is over here. My alternate one's going to be over to the right side. So my critical value was 7.78. 7.78. Is that 7.78 is my critical value? Is the test statistic in the HO section or the H1 section? Well, my test statistic is 12.86. 12.86 would be bigger than that number, so my 12.86 is going to be my alternate hypothesis. So my alternate hypothesis is that it's not independent and it does have a relationship. So it says, can we reject the hypothesis that there is no relationship? Can we reject that there's no relationship? Yes, we can, because we're saying it does have a relationship. So if we're going to reject that it has no relationship, then we're going to accept that it does have a relationship. I hate the one when they use the reject and not the accept the claim. I'm going to reject this one. Can we reject that one? Yes, we can. All right. Number 8. Another one of these big long ones. It says an undergraduate student who won an award for his study of student diagnosed with ADHD, attention deficit hyperactivity disorder. He showed that the students with ADHD performed slightly differently on visual search tasks than did students who didn't have ADHD. The display he used for his search task contained about 20 letters positioned in various locations and orientations on a computer screen. The letters and the positions varied from trial to trial. The task of the participant on each trial was to determine with in 2 seconds whether or not particular target letters appeared among the 20 letters. Each trial resulted in either a hit, the target appeared and the participant identified it, or a miss, the target appeared and the participant did not identify it. A false alarm, there was no target but the participant stated there was, or a correct rejection, there was no target and the participant stated this fact correctly. While attempting to get a study published in an academic journal, the student was confronted with the following criticisms. Since he had used colored letters and backgrounds in his displays, couldn't the presence or absence of color vision in the participants have produced some of the effects seen in the data? The student went back and tested his participants for color blindness and reanalyzed the data. So again, we're going to have a contingency table. It gives a summary of 2,000 trials of the experiment. Each trial was performed either by a colorblind participant or a non-colorblind participant. Each cell of the table contains 3 numbers. The first number is the observed frequency. The second one is the expected one that we're going to do some calculating on. And then we're going to have our formula that we have to figure out our observed frequency minus our expected frequency squared divided by the expected frequency. So, whoa, it went all the way back to number 4 instead of number 8. 7, 8. Here's my tables for number 8. So, again, when we do number 8, the first column is like we did, or the first row is like we did on problems number 1, 2, and 3. So, this first one's on the top ones. That looks weird. I'm going to move it down a little bit. This one and this one. We are using our formula row total times column total. I don't know why I keep underlining that. Divided by the total sample size. So again, I'm going to do all those ones in blue, and so that way you know those are all those calculations. So, first box we have to fill in, our row total is 202. 202 times our column total, 672, divided by our total sample size, 2,000 were surveyed. So 202 times 672 divided by 2,000. If you do that calculation, you get 67.87. These ones say round the first column to 2 decimal places, or the first row to 2 decimal places, the second one to 3. So we're going to round that off to 67.87. I'm going to go over and do this one. This one here, row total is 202. Column total is 722. Divided by our 2,000. So row total 202 divided by column total 722 divided by 2,000. Rounding that off to 2 decimal places, 72.92. 72.92. On the not colorblind, the row total 1,798 times the column total 672 divided by the sample size 2,000. So 1,798, that says 98, yep, divided, or times 672 divided by 2,000 should give you 604.13. 604.13. last box of this one over here, my row total, 1,798. My column total, 722, divided by my sample size, 2,000. I should come up with 649.08. 649.08. Now, the next ones. The next ones is my formula. On my formula that I did, FO minus FE squared divided by FE, right? It's that formula we've been calculating all along. So, on the first one, we have 59 minus 67.87. 59 minus 67.87. I'm going to square that and divide it by the 67.87. Again, these ones we're going to round to 3 decimal places once we punch them into our calculator. So 59 minus 67.87, square that, divide it by 67.87, and we should come up with 1.159. 1.159. The next one over here on the end, we're going to take our observed frequency of 69 minus my expected frequency of 72.92 squared divided by the 72.92, which is my expected frequency. If we go ahead and do that calculation, we should be coming up with 0.211. 0.211. The next one, our observed is 613, our expected is 604.13. So 613 minus 604.13 squared divided by the 604.13. The observed minus the expected squared divided by the expected. And again, we're rounding off to 3 decimal places. So we should get 0.130. 0.130. Make sure you're trying to punch those in and come up with the same numbers I'm coming up with, so you have practice putting them in your calculator. Last one here, I am going to go ahead and find the value here. I'm going to take my observed, 653, minus my expected, 649.08. That is squared and divided by the 649.08. When you punch that into your calculator, you should come up with 0.024. 0.024. Second table. Type of test statistic, we now know it's chi-squared, our degree of freedom. The degree of freedom. The number of rows minus 1 times the number of columns minus 1. We have 2 rows, so 2 minus 1. We have 1, 2, 3, 4 columns. So 4 minus 1. So 2 minus 1 is 1. 4 minus 1 is 3. 1 times 3 gives me 3 degrees of freedom. So the number of rows is 2. 2 minus 1 is 1. The number of columns, we have 4 different columns. 4 minus 1 is 3, and then 1 times 3 is 3. The value of our test statistics. Add all the FO minus FE squareds divided by FEs. So I'm going to add 6 numbers here. 8 numbers. 1, 2, 3, 4, 5, 6, 7, 8. all of those numbers I circled, we're going to add all of those up. So 1.159 plus 1.780 plus 0.950 plus 0.211 plus 0.130 plus 0.200 plus 0.107 and 0.024. So those four numbers that I circled, we're going to add all of those up. That's going to be the value of our test statistic. And if you add those up, you should get 4.56. 4.56 should be your total. We are going to find the p-value on this one. The p-value instead of the critical value. So we're going to do p of chi squared is greater than our test statistic, 4.56. Whoops, I forgot my degree of freedom then. Degree of freedom, 3, right? Don't forget to put that in there. You'll see it when you use the Alex calculator. 4 chi squared greater than 4.56 with a degree of freedom of 3, p of. So we should come up with 0.207. 0.207 is my p-value, my percentage. Again, when I am looking at this, we have our null, we have our alternate one. This one is that it is independent. This one is that it's not independent. So if it is independent, we have to remember there's no relationship. If it is not independent, we know there is a relationship. So when we do our test statistic, since we're doing the p-value, we're comparing this percent to the level of significance. 0.207 compared to 0.05. 0.207 is going to be greater than 0.05. If my p-value is greater than my level of significance, we accept the null, right? This is my true statement. This is my true statement. So, can we reject? There is no dependence. Can we reject there's no dependence? No, we can't reject that. That's the true statement. The true statement is saying there is no relationship. So can we reject that? No, we can't reject that. Can we reject there is no dependence? No, we can't. We're going to say there is a dependence because there's no relationship. One last one on here. Number 9. Among the huge body of literature on smoking are data detailing the relative successfulness of males and females in quitting smoking. Study of 400 adults ages 20 and older who began various smoking cessation programs produced the data in Table 1 below. In the table, less than 2 weeks means that the individual returned to smoking within 2 weeks beginning the program. Between 2 weeks and 1 year means the individual survived the first 2 weeks but returned to smoking within a year. And at least 1 year means the individual did not smoke for at least a year after beginning the program. Table 1 is a contingency table for whose cells contain 3 numbers. The first number in the cell is the observed frequency, second one is the expected one, and then the third one there we have to figure out using our formula. So the first ones we're rounding to 2 decimal places, the second ones to 3, and then we're going to check at a 0.5 level of significance. Is the assumption that there's no association between the sex and the length of the smoking cessation period. So if we go to our tables so we can fill in our tables. Number 9, that should be the last one. There we go. So on number 9 here, Again, we are filling in the top ones using the formulas from problems number 1, 2, and 3. So, the row times the column divided by the total sample. So, my row total, 245. My column total, 97. Divided by my total sample, 400. $245 times 97 divided by 400. Again, we're rounding the top ones to 2 decimal places, and so we should get 59.41. The next one, my row total, 245. My column total, 208. Divided by my sample size, 400. So 245 times 208 divided by 400 should give you a value of 127.40. 127.40. The next one's moving down to the females. My row total, 155. Almost looks like a 1. My column total for the first column is 97. My sample size, 400. So 155 times 97 divided by 400 should be 37.59 when you do that calculation. 37.59. And then the next one, my row total is 155. My column total is 208. And I'm going to divide that by my 400. And I should come up with 80.60. 80.60 goes there. The bottom rows. The bottom rows we're using our formula. So we're doing FO minus FE squared over FE. So the bottom ones we're going to do in green just so you can see where those came from. So observed frequency is 53. Expected frequency was 59.41. We've got to square that and divide it by the 59.41, which is our expected frequency. So 53 minus 59.41, we're going to square that and then divide by the 59.41. These go to 3 decimal places. So 0.692 should be what you get. 0.692. On the next one, my observed is 134. 134 minus 127.4 squared divided by my 127.40, which is what I got for my expected frequency. So 134 minus 127.4, square that, and then divide it by 127.4. You should come up with 0.342. 0.342. The next one, our observed is 44. So 44 minus the expected of 37.59 squared divided by our 37.59. The observed minus the expected squared divided by the expected. So 44 minus 37.59 Square that, and then divide by 37.59, you should get 1.093. 1.093. And then the next one, my observed is 74. 74 minus my expected, 80.60 squared, divided by my 80.60. So the 74 minus 80.60 squared, divided by your 80.60. And you hopefully come up with 0.540. 0.540 is what you should come up with. Table 2, again, wants to know the type of the test statistic. We know that it's chi-squared and we have to have our degree of freedom. My degree of freedom, the number of rows minus 1 times the number of columns minus 1. I have 2 rows, male or female. 2 minus 1 is going to give me 1. Columns, less than 2 weeks between 2 and 1 year, at least 1 year. I've got 3 columns. 3 minus 1 is 2. So I've got 1 times 2. 1 times 2 then gives me 2 degrees of freedom. The value of my test statistic. When I find the value of my test statistic, I'm going to add all of the ones in the FO minus FE squared over FE. So I'm going to add this one, plus 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 this one. Do not forget to add in the ones you didn't actually calculate. They're still part of your table. They just saved you some work. So I'm not going to write them all down, but on your calculator, 0.692 plus 0.342 plus 0.001 plus 1.093 plus 0.540 plus 0.001. Add all 6 of those up. You should come up with 2.67. We are going to do the critical value. So we're going to do the critical value. We're going to do chi-squared sub 0.05 with a degree of freedom of 2, right? Chi-squared sub 0.05 with a degree of 2. Have to use your Alex calculator to do that one. Chi-squared sub 0.05 with a degree of freedom of 2 gives us 5.99 for our test value. So again, HO is here, H1 is here. Our critical value is 5.99. We're figuring out where our test value belongs. Is our test value smaller or bigger than my critical value? Well, my test value is 2.67. 2.67 means I'm in the section with the null, right? So if I'm in the section with the null, this is the independent, this is the not independent. So if it's independent, we're going to say there's no association. If it's not independent, there is an association. So, independent. If you're independent, you're not associating with something else. Not independent, you are associating with something or someone else. So in this case, our null is where we're at. We're going to say that is independent, that there is no association. The question says, can we conclude that there is an association? No, we said there is not an association. So can we conclude that there is one? We certainly cannot. No, there is no association. All right, that's the end of chapter 11.